In this video, I'm going to talk about question 6 from each of the first 4 problem sets. Question 6 is numerically approximate the solution of the integrating fire initial value problem of the form this, where you're given the constant EL is minus 75, tau m is 10, or m is 10, IT is just 0.0 times t, and you have an initial condition of minus 50, V of minus 50 is minus 75, and the step size of 0.5. And I've asked you to look at, for the Euler method, which I've done, but I'm going to redo, the second order Taylor, the Hewn method, which is a second order Runge-Kutta, and the two-stepped Adams-Bashford. So the one thing that is general for everything is the discrete domain. So that's the first thing I'm going to do. So our discrete domain is from minus 50 milliseconds less than or equal to t less than or equal to 400 milliseconds. It doesn't really matter, that's milliseconds, just from minus 50 thing. And we're given h is equal to 0.05. So what's our n? N is equal to 400 minus 50 divided by 0.5, which gives us our n goes up to 900. And so that gives us t0 is equal to minus 50, t1 is equal to minus 50 plus 0.5, and all the way up to t900 is equal to 400. Or generalizable, ti is equal to minus 50 plus 0.5 times I, for I is equal 0 to 900. And so now we have the discrete domain that we'll use for all 4 methods. So the simplest method is the Euler method. As we know, the Euler method is just wi plus 1 is equal to wi plus h times ft comma wi. Now, our equation, I'm going to rewrite it and bring the tau over dv dt, is equal to minus v minus el plus or m times it, I a function of t, divided by tau m. So that gives us f t comma v is equal to minus v minus el plus or m it divided by tau m. And we know that el is equal to minus 75, or m is equal to 10, tau m is equal to 10, and it is equal to 0.01 t. So I'm going to sub all that in just to make it a bit easier. Oh, I'm going to call this FIF, just to refer to integrating fire. This will make more sense when the code is implemented. So FIF is equal to V plus 75 because minus minus, plus 10 times 0.1 t, all divided by 10. And so that's just equal to minus V plus 75 plus 0.1 t divided by 10. So our Euler method for this, and I'm going to use the Euler I plus 1. So what we don't know is equal to Euler I plus our step size h times f if ti comma Euler. I. So that's the general form of it. So that's Euler is known, Ti is a given, H is a given. So we know everything on the right hand side. And if we want to write out in full, what we have is the future, and this is for I is equal to 0 to 899. So so in the specific, that's equal to Euler I plus 0.5 times minus, bring that minus up to make sure, minus Euler, which we know, Euler I plus 75 plus 0.1 times Ti all divided by 10. And that there is our Euler method. Very straightforward. It works quite well. And of course, I didn't state, to emphasize, our initial condition is Euler 0 is equal to minus 75. So now I'm going to set up the second order Taylor. Once again, we have to start with our function. So the general second order Taylor is the form that wi plus 1 is equal to wi plus h times f t comma wi plus h squared 2 times f dash t comma wi. So that's our general second order Taylor. So we need a few things. We know what f is, so we've already defined f, and for our specific integrating fire model, it's equal to minus v. I should emphasize that f is a function of t and v, is minus v plus 75 plus 0.1 times t all divided by 10. So that's our f. So to calculate f dash, we need to differentiate this. So f dash if t comma v is equal to minus v dash plus 0 plus 0.1 all divided by 10. We have an issue here because we have a v dash, but by definition from our formula, v dash is equal to f if t comma v. So that gives us f dash if t comma v is equal to minus bracket f if t comma v plus 0.1 all divided by 10. So now let's write our form for the Taylor. Here I'm just going to call it Taylor. So the future Taylor of I plus 1 is, oops, that should be in red. The future Taylor, I plus 1, is equal to the current Taylor plus h times fi f ti comma Taylor I h plus h divided by 2 squared f dash fi ti comma Taylor I. So what does that look like in our case? So that's equal to Taylor I plus 0.5. Now this first part will be identical to the Euler method, except we have the word Taylor. Minus Taylor I plus 75 plus 0.1, that's round brackets, plus 0.1 Ti, all divided by 10, plus 0.5 squared divided by 2. And now we go back to this, which is minus all bracket Taylor minus Taylor plus 75 plus 0.1 plus 0.1 Ti, that's that, minus all divided by 10 plus 0.1 divided by 10. And so now we have our method. Once again, I is equal to from 0 to 899. Okay. Next, the Hewn method. The Hewn method, as I stated, is a version of the second order Runge-Kutta. And so it says, the general form says that Wi plus 1 is equal to Wi plus h divided by 2, k1 plus k2, where k1 is equal to ft comma wi, and k2 is equal to fti plus h, or fti plus 1, comma wi plus h k1. So once again, in our specific scenario, we have Hewn future point is equal to the Hewn current point plus 0.5 divided by 2, k1 plus k2. Now, k1 is equal to FIF of Ti, comma, Hewn I, which we know is equal to minus Hewn I plus 75 plus 0.1 Ti, all divided by 10. So that's the same once again as the Euler. K2, which equals to F integrating fire, Ti plus H, or Ti plus 1, Hewn I plus H times K1. So this is a bit more involved. That's equal to minus Hewn I plus H times K1 plus 75 plus 0.1 times Ti plus H, all divided by 10. And that's it. And now we have, that's for I is equal to 0 to 899. So the very last method is the two-step Adams-Bashford. The general two-step Adams-Bashford is Wi plus 1 is equal to Wi plus h divided by 2, fti Wi, that's 3 times that, minus fti minus 1, Wi minus 1. So we need two steps. So in all the previous steps, we always knew what W0 was equal to minus 75, or the initial condition. So we needed W1. And you can take that from the Hune or the others, and we'll come back to that in a second. So the Adams-Bradford future is equal to the current bit of information plus our step size of 0.5 divided by 2, square bracket, 3 times F integrating fire, TI ABI, bracket, minus F IF TI minus 1, comma, AB I minus 1. Of that form. So to write out in full, which I will, and then we'll talk about how it's simpler to leave it in function form. ABI plus 0.5 divided by 2, 3 times minus ABI plus 75 minus 0.1 TI all divided by 10 minus AB I minus 1 square bracket plus 75 minus 0.1 TI minus 1. That bracket there, that's the large bracket, and that's all divided by 10. Square bracket. So the issue with this is, as I said, unlike all the others, this is for I is equal to 1 to 899. We know that AB 0 is equal to minus 75. So therefore we need AB1. And I would just take the Hune solution we have already and put it in. And that would be that. So that's the setup for all four methods. And in the next